Alright, in today's video we're looking at solution stoichiometry problems. These are for grade 11 chemistry, regular or advanced, as an introduction to the topic. So question number 1 is a straightforward example. We're asked what mass of aluminum metal would be needed to react completely with 35 milliliters of 2 molar hydrochloric acid. If you think you know what you're doing, you can pause the video and try the question yourself. So as with any stoichiometry problem, we need to have a balanced chemical reaction, right? We have to have an equation that's balanced, otherwise we don't have the right ratios for solving the stoichiometry problem. So to balance this equation, as you can see we've got, I'll put a 6 in front of the HCl, I'll put a 2 in front of aluminum, a 2 here, and a 3 here. Okay, so there's a balanced chemical equation: 6 hydrogens, 6 hydrogens, 6 chlorines, 6 chlorines, aluminums, and we're good. Alright, so now I'm going to solve this using a string of unit multipliers. I'm going to start with the volume of the acid. The reason I'm starting with the volume is because I know what its concentration is, and I'm going to use the concentration, the molarity, as a unit multiplier. When I start with a string of unit multipliers in my answer, I generally don't start that string with the unit multiplier, so I'm going to start with the volume instead. 35.0 milliliters of the hydrochloric acid. Now, since molarity, the concentration, is moles per liter, let's take that molarity, the volume, and switch it to liters of HCl. Now we can use the concentration to switch the liters of hydrochloric acid into moles of hydrochloric acid. Moles per liter is concentration. And then here comes the stoichiometry, the reason we needed the balanced equation. We can convert the moles of the HCl into, we're trying to find mass of aluminum, so let's switch to moles of aluminum, and that's going to be using the coefficients. And finally, we were asked for grams, so we'll convert the moles of aluminum back to grams of aluminum, and we'll have the answer to the problem. So the volume, 1 liter, is 1,000 milliliters. The concentration of the acid was 2.0 molarity, so that's 2.0 moles per liter. Now watch your significant digits. Don't throw away that 0. It's 2.0, 2 digits. From the balanced equation, we can see 2 moles of aluminum will react with 6 moles of hydrochloric acid. And from a periodic table, 1 mole of aluminum has a mass of 26.98 grams, its molar mass. Grabbing a calculator and multiplying and dividing as needed, we're going to keep 2 digits in our final answer because of this concentration, 2.0. It had the smallest number of significant digits. Remember that the coefficients are considered pure numbers. They're not measured quantities, so you don't use them to round off your answer. So doing this on a calculator, you'll see the final answer is 0.63 grams of aluminum is needed, I guess. That's a good phrase. Is needed to react with our acid. Okay, so that 35 mL of hydrochloric acid would dissolve 0.63 grams of aluminum metal. Question number 2. What volume in milliliters of 0.75 molar calcium nitrate would react completely with 148 grams of sodium carbonate? So this is a similar question to the one we just did, but instead of giving us the volume and the concentration and asking what mass will react with it, we're doing this the opposite direction. We're given a mass of sodium carbonate, and we want to know what volume of the other reactant, the calcium nitrate, would react with it. So we'll assume the calcium nitrate is a solution, 0.75 molar, and the sodium carbonate must have been a solid. We're measuring out 148 grams. So again, we start by balancing the chemical reaction. In this case, it's pretty easy to balance. We just need to put a 2 in front of the sodium nitrate. And again, if you think you know what you're doing, you can pause the video and try to set up the answer yourself. So I'm going to start now with my mass of the sodium carbonate. The concentration is a unit multiplier for calcium nitrate, but we don't know its volume, we don't know its moles, so we really can't use it yet. But the grams of sodium carbonate, in my head I'm already anticipating I could convert that to moles. Then using my balanced equation, I can convert that into moles of the other reactant. So I can go somewhere if I take that mass as my starting point. So 148 grams of the sodium carbonate, Na2CO3. I'll convert the grams to moles of sodium carbonate. Then using the balanced equation, stoichiometry, we can take the moles of sodium carbonate and we can convert that to moles of the calcium nitrate that we're interested in. And we were asked what volume of the calcium nitrate because it's a solution, and we have its concentration, which is 0.75 moles per liter, 0.75 molarity. So therefore we can take the moles of the calcium nitrate and we can switch that to liters of calcium nitrate. And finally it asked for the answer in milliliters, so let's just switch our liters to milliliters. So from a periodic table, we need the molar mass of sodium carbonate. You can look that up. 1 mole will weigh 105.99 grams. From the coefficients in the balanced equation, there's 1 mole of calcium nitrate will react with 1 mole of the sodium carbonate. It's a 1-to-1 ratio. The concentration of the calcium nitrate, moles per liter, was 0.75, so 0.75 moles per liter. And then there's 1,000 milliliters in a liter. Alright, so therefore we grab our calculator. We're going to keep again 2 significant digits in the answer. The calculator spits out an answer of 1,862 milliliters, approximately 1862. So I'm going to round that off to 2 digits, and I'll put it in scientific notation. I'll call it 1.9 times 10 to the power of 3 milliliters of the calcium nitrate solution. So 1,862 milliliters gets rounded up to 1,900 milliliters and then expressed in scientific notation with 2 significant digits. The third example is getting a little bit more complicated because now instead of a mass and a concentration, we're given 2 solutions. And so one of the solutions we know its volume, sulfuric acid, 0.5 molar, and 275 milliliters of 0.5 molar sulfuric acid. And the other solution, we know its concentration, 0.75 molar sodium hydroxide, but we want to know how much of that would we need to react with to neutralize this sulfuric acid. Don't let the word neutralize bother you. It's just the specific term you would use when an acid, in this case sulfuric acid, is reacting with a base, sodium hydroxide. It's called a neutralization reaction. So we need to write the balanced equation since it wasn't given to us at all here. So sodium hydroxide is NaOH. You might need to use your data booklet to refresh yourself on the charges and the formulas of the ions involved. Sulfuric acid would be H2SO4, and this looks to me like a double replacement reaction. Sodium's charge is +1 and sulfate is -2, so the salt produced will be Na2SO4, and then the hydrogens and the hydroxides will make water. So there's the double replacement reaction. To balance this, we'll need 2 moles of sodium hydroxide for every 1 mole of the acid, and that's going to make 2 moles of water and 1 mole of sodium sulfate. So there's our balanced chemical equation. So now we're wondering what volume of the sodium hydroxide solution will be needed to react with, to neutralize, 275 mils of 0.5 molar sulfuric acid. So there's 3 different numbers in that question. The one I'm going to start with again is the volume, 275 milliliters, of the sulfuric acid, and that's because we know its concentration also. So if I start with its volume, I know I can convert that to moles, and then I can start going on a path of stoichiometry. Now, if I want, I can switch the milliliters to liters, because molarity is moles per liter. However, in this question, we have two solutions, and we're given the volume in milliliters for one of them, and we want to know the volume in milliliters of the other that will react with it. Since everything here is in milliliters, I'm going to not switch my units to liters. I'm going to leave it with milliliters. And so what I'll do is I'll convert my milliliters of sulfuric acid into millimoles of sulfuric acid. You recall that concentration, moles per liter, is the same as millimoles per milliliter. So when we see 0.5 molarity, that's 0.5 moles per liter. It means also that there's 0.5 millimoles of sulfuric acid for every milliliter. If that really bothers you, then just go ahead and convert the milliliters to liters and then use moles instead of millimoles. My balanced equation, I can see the ratio between the millimoles of the sulfuric acid and the millimoles of the sodium hydroxide that I'm using. It's going to be a 2-to-1 ratio. And then using the concentration of the sodium hydroxide, we can convert the millimoles of sodium hydroxide back to milliliters of sodium hydroxide, which is what we're trying to find, what volume of the sodium hydroxide will react with the 275 mils of the acid. So the acid's concentration was 0.50 millimoles for every milliliter. The balanced equation tells me 2 millimoles of the sodium hydroxide will react with 1 millimole of the sulfuric acid, and the base concentration was 0.75 millimoles for every milliliter, 0.75 molarity. So grabbing a calculator, and again we're going to keep two significant digits in this answer because there were two significant digits in these two numbers here. When you're multiplying and dividing with measured numbers, round off your answer to the smallest number of significant digits that was being used in the calculation. So I'm going to use my answer on my calculator is 367 milliliters of sodium hydroxide, but I'll round that up and express it in scientific notation, 3.7, two digits, times 10 to the power of 2 milliliters of sodium hydroxide. Alright, stoichiometry problems. I hope this is bringing back some good memories as a review as we get closer to our exam. Question number 4, take a moment and read that and see if something jumps out at you. Do you notice that in this question, not only is it a stoichiometry problem, but this one looks like it's going to be a limiting reagent stoichiometry problem. We have ammonium phosphate reacting with calcium nitrate, and we want to know how many grams of precipitate will be formed. This question is actually a little bit harder than the ones we've been doing because we're told the volume and concentration of each reactant. Right? When you're told how much you have of each reactant in the reaction, that's a hallmark that this is a limiting reagent problem. We're going to have to stop and figure out which one of those two reactants is limiting, which one will get used up first in the reaction and therefore stop the reaction. Once one of them is used up, you can't make any more products. Once we know the limiting reagent's identity, we can use it to answer the question, how many grams of precipitate will form. Now you notice the question actually didn't identify the precipitate, so we're going to have to use some solubility rules. And again, it doesn't have a balanced equation, so we're going to have to write a balanced chemical equation as well. And then finally, we've got this added wrinkle that there's only 65% yield to this reaction. So there's several things in here that make this a little bit more complicated than what we've been doing. So let's start to be, I think you know what you're doing. Pause the video and jump in and try it. So I'm going to need a balanced chemical equation. Ammonium phosphate. Ammonium is NH4 positive, and phosphate is PO4 3 negative. So I'm going to need 3 of those ammoniums, so NH4 in brackets, subscript 3, with the phosphate, PO4. And it's reacting with the calcium nitrate. Calcium is 2 positive, an alkaline earth. Nitrate is a complex ion, NO3 negative. Since calcium is 2 positive, I'm going to need 2 of my nitrates to go with that. Now these were solutions. I haven't been putting in phases, but I'll put phases in here. These are aqueous and aqueous because they're dissolved in water. Now this looks like a double replacement reaction, right? So we're going to trade partners. Ammonium plus 1 is going to go and grab nitrate minus 1. So plus 1 minus 1, that's an easy formula, NH4NO3. The other product will be calcium phosphate. Calcium is plus 2 and phosphate is 3 negative. So I'm going to need 3 of the calciums, Ca3, and 2 of the phosphates, PO4, 2. Now, what are the phases of those two products? Because we have to figure out which one will be the precipitate. According to our solubility rules, any salt that begins with ammonium, or any salt that ends in nitrate, this one actually has 2 different rules that apply to it, those are soluble in water. They're highly soluble. So therefore the ammonium nitrate is going to be dissolved. It'll be aqueous. However, most phosphate salts, according to our rules, are not very soluble. They're sparingly soluble. So the calcium phosphate is going to be a precipitate. There are some exceptions to that rule, the alkali metals and ammonium exceptions, but calcium is not one of the exceptions. So there we've identified the precipitate is going to be calcium phosphate. So we're asking how many grams of that will be formed, and then we know we still have this 65% yield. So now let's figure out which one of these is limiting. So which one is the limiting reagent in the question? To do that, I'm going to just pick one of the 2 reactants. It doesn't matter which. I'll take the first one, and I'm going to use its volume as my starting point, 100 milliliters of ammonium phosphate. Now I don't want to write, these formulas are rather complicated. I'm going to just abbreviate ammonium phosphate as AP. Alright, so 100 mils of ammonium phosphate. And I'm going to go calculate the volume, because we know the volume here, the volume of calcium nitrate that will be needed to react with this. Once I know how much calcium nitrate is needed to use up the ammonium phosphate, I can compare that to how much we have, and I can decide whether or not the calcium nitrate is in excess or whether it's limiting. Okay, so let's try this. And again, I'm going to use millimoles in my answer. If you really want to use moles, then go ahead and convert this to liters. But I'm going to convert my millimoles of the milliliters of ammonium phosphate to millimoles of ammonium phosphate. Then I can use the balanced chemical equation. I just realized I didn't balance it. We can convert the millimoles of ammonium phosphate to millimoles of the calcium nitrate. And then, using its concentration, millimoles of calcium nitrate can be converted to milliliters of calcium nitrate. And then we can use this to compare to how much we have. So there's the milliliters of calcium nitrate are needed. Now let's go back and balance our chemical equation. I see that there's 2 nitrates and 3 ammoniums, and they're going to make ammonium nitrate, so they're going to have to be equal. So I'm going to put a 2 here to give me 6 ammoniums, and I'll put a 3 there to give me 6 nitrates. That's going to give me 6 ammonium nitrates. And then 3 calciums and 2 phosphates. There you go. There's my balanced equation. So now I can take the concentration of ammonium phosphate. It was 0.350 molarity, so there's 0.350 millimoles for every milliliter. The balanced equation says that 3 millimoles of calcium nitrate reacts with 2 millimoles of ammonium phosphate. And then the calcium nitrate's concentration was 0.125 molarity, so 0.125 millimoles for every milliliter. Grabbing a calculator and evaluating that, I get 420 milliliters of calcium nitrate would be needed to use up all of the ammonium phosphate. Now, how much calcium nitrate did we have? Well, we had only 225 milliliters, but we need 420. So since we don't have enough, calcium nitrate, so the calcium nitrate is going to get used up. So it's going to be the limiting reagent. The limiting reagent, the reactant that gets used up and therefore stops the chemical reaction and determines how much product we can make. So since the calcium nitrate is limiting, we need to start the answer to the question, how many grams of precipitate, we need to start with the limiting reagent. So I'm going to take the 225 milliliters of calcium nitrate that we have, and we're going to use its concentration, which was again 0.125, to switch the milliliters to millimoles of calcium nitrate. Then, using the stoichiometry of the balanced equation, millimoles of calcium nitrate, we can convert that to millimoles of the precipitate, millimoles of the calcium phosphate. Now the question was asking for mass, so I'm going to switch my millimoles of calcium phosphate back to moles, only because I'm going to express the answer in grams. And then moles of calcium phosphate, we can convert you to grams of calcium phosphate using its molar mass. Now, if this is where I stop, I'm assuming something about the reaction. If I stop here, I can calculate how many grams of calcium phosphate should form. But the assumption I'd be making there is that the reaction has 100% yield. Okay, the answer, as I've set it up now, assumes 100% yield. In other words, it assumes that every atom, every formula unit rather of calcium phosphate that we're supposed to make, we're going to actually get. Okay, so we're not going to spill anything, we're not going to leave anything in our beaker, if we're filtering, we're going to perfectly dry out the filter paper afterwards, nothing's going to go through the filter paper. There's so many assumptions in that. But we know that this is not 100% yield. This is only a 65% yield process. So you're going to be losing quite a bit. You're losing about 35% of the calcium phosphate. So I'm going to take my answer and I'm going to use that percent yield. So since I don't get 100%, I only get 65%. So I'm going to multiply my answer by 65 over 100, 65%, to tell me how much I will get with that 65% yield. So this many grams of calcium phosphate will form, or will be recovered, is perhaps a better way to say it, will be recovered, will be collected. Okay? So now we can use the concentration of the calcium nitrate was 0.125 millimoles per milliliter, 0.125 molarity. From the balanced equation, we can see that there's 1 mole of calcium phosphate for every 3 moles of the calcium nitrate. And then to switch millimoles to moles is just like switching milliliters to liters. In 1 mole, there's going to be 1,000 millimoles. And then using the molar mass of calcium phosphate from a periodic table, there's 310.06 grams for every mole. Alright, so if you go ahead and multiply through all there, you're going to find out that there's 1.89 grams of calcium phosphate that can be recovered. Now some people wouldn't have tacked on that 65% at the end. They would have simply calculated that you could make 2.91 grams of calcium phosphate, assuming 100% yield. Then they would take the 2.91 grams, that was assuming 100% yield, and they'd times that by 0.65 because it was 65% yield, and they would get the same answer. Alright, so there's another way to approach that. Alright, so that was the more complicated question involving limiting reagents, involving solubility rules, percent yield. That's a good, if you understand that question, you're doing pretty well in this unit on solutions in grade 11 chemistry. So I hope that helps. Good luck working on your assignments and or studying for your exam.